Okay, this presentation is over colligative properties. The colligative property that we're going to be focusing in on this presentation is going to be freezing point depression and boiling point elevation. How do these properties come about? Well, we're looking at a solution, and remember that a solution is made up of two parts. It's made up of the solute and it's made up of the solvent. So here, how do we lower the freezing point or how do we increase the boiling point of a solution? Well, that's going to depend on the solute that's placed into the solvent, right? So if I look at calcium chloride, for example, I get calcium ion 1 plus 2 chloride ions, giving me 3 total ions overall. Sodium chloride only gives me 2 ions because I get 1 from the sodium and 1 from the chloride ion. And then if I look at a type of sugar here, whenever it dissolves into a solvent, I get one molecule, and that's true for any kind of covalent compound that you might run into. So it doesn't really depend on the identity of the solute. It just depends on the amount of ions or molecules that are produced, and that'll change my freezing point or my boiling point of a pure solution, right? So here, there could be many compounds that will give me 3 ions. So for example, magnesium chloride, right, would give me also 3 ions. There's many compounds that would give me 2 ions. You know, lithium fluoride would give me 2 ions here. So it doesn't depend on the identity, where I'm getting the ions from. It just depends on how many ions or how many molecules are being produced. Again, two type of colligative properties are going to be freezing point depression, which is a symbol of delta TF, and then boiling point elevation, which is a symbol of delta TB. So for example, if I look at water as a pure substance, it has a freezing point of 0 degrees Celsius. If I were to add one of the ionic compounds or one of those sugars into the water, then it's going to lower that freezing point of the water to something below zero. For boiling point, that boiling point of a pure solvent, for example, for the water again, is 100 degrees Celsius. So if I add some kind of ionic compound or some kind of a sugar that dissolves into this water, it's going to elevate, it's going to increase that boiling point to over 100 degrees Celsius. So let's look at what's going on here. So again, water as a pure substance has a temperature of 0 degrees Celsius when it freezes. Okay, again, what's holding that water together? What those intermolecular forces that we discussed earlier in this semester, those hydrogen bonding, London dispersion forces, dipole forces, and you will remember also that we talked about that there's a certain equilibrium between that liquid and solid state. So here, whenever water's in the pure state, um, those intermolecular forces transitioning from a liquid down to a solid, they'll reset equilibrium at 0 degrees Celsius. What happens to water when we add a ionic compound or some kind of sugar that either dissolves or dissociates in there? Well, these particles here are now in between those water particles. So the intermolecular forces that would occur normally at 0 degrees Celsius now are interrupted. These particles are getting in between that, so they kind of have to be pushed out of the way so that the water can transition from a liquid down to a solid again. So there's a new equilibrium that that has occurred, and because of that, it's going to lower that freezing point, let's say from 0 down to -5. Now, this is a totally made up number. I'm just giving you for instance, an example, right? Let's look at the boiling point here. So for pure water, again, it's going to boil at 100 degrees Celsius. So there's an equilibrium here with the kinetic energy between the particles that make up the liquid and the particles that make up the gas. And whenever that equilibrium is reached, whenever these kinetic energies of these two liquid and gases are equal, right? The water can start to evaporate off. And so those intermolecular forces are overcome at 100 degrees Celsius. When I look at adding a ionic compound or a salt, excuse me, or a sugar compound that's dissolved into the water, then it's going to elevate. Those intermolecular forces have to absorb a little bit more energy than they normally would so that they can evaporate and become a gas. So there's going to be a new equilibrium that's set here in the on the container on the right side because of the addition of these either ions or these molecules that are in there. So it could increase the temperature to, let's say, 105 degrees Celsius. So what are some type of applications here for colligative properties? So whenever, it gets cold around San Antonio, and this not all the time, but every now and then when it does, it gets really cold. Water may accumulate on the roads, and to prevent the water from freezing at 0 degrees Celsius, right? They add these salts to that water, and it's going to lower that freezing point so that it's still safe for us to drive on the road, even though we've reached the point where water would freeze. And then making ice cream. Again, ice creams they put them usually in these containers that are inserted into these vats that are surrounded by salty water. Lowers the freezing point, allows the ice cream to be made a little bit more quickly. Antifreeze in cars. Um, this functions for two reasons. Excuse me. Um, it allows the water that's inside of the radiator to freeze at a much lower temperature, and it also works whenever the engine is hot. It allows that water to boil away at a much higher temperature, so it can absorb heat coming away from the engine, put it in the radiator, cools it down, and then sends it back through. Fish and insects use the same concept as well. They have what are like particles in their fluids inside their body that will lower the freezing point so that whenever it gets really cold, they don't die because their cells are bursting, right? So fish and insects can survive these really extreme cold conditions by having these types of molecules, these ions or sugars that are dissolved into the liquids of their bodies so that they don't freeze over. So how do we calculate the freezing point and the boiling point of a solution when we put some kind of a salt or some kind of a sugar into water? Well, first of all, if I see aqueous, I didn't write that very well, but let me write it again. If I see AQ, that means that that I dissolve that solute into a solvent, which is water. And looking at these symbols here, I know that delta T is going to be a change in temperature, and that could be for either freezing or it could be for boiling. K is a constant that's going to be given to you in degrees Celsius over molality. And then you may have to calculate the molality of a substance. Sometimes it's given to you, sometimes you have to calculate it, but that's moles over kilograms. So moles of the solute over kilograms of the solvent. And then you have the number of particles. And remember that that can be either ions or that can be molecules. And let me redo that because that looks pretty ugly. And that goes back to the very first slide that I talked about here with this one. So that N is going to be determined by how many ions were produced from the dissociation or how many molecules are produced from the dissolving. Remember that molecules, no matter what it is, it's always going to give me one. And for the ionic compounds, it's going to be determined by that number of subscripts that I have behind each one of the symbols. So here again, calcium is 1, chlorine was 2, so that's why I had a total of 3. 2 plus 1 is 3. For sodium chloride was 1 and 1, so that's why it was 2 ions. So this is the end of the presentation here. I'm going to stop right here, and I'm going to work on two problems that I'm going to put on a separate document and paste them or put them, excuse me, post them on the Google Classroom.